All right, I have some homework back for you today. So you can be passing that around. And we all had a long weekend. Monday was a holiday, so here it is Tuesday, and we've got an assignment due Thursday, our second one. So anyway, I have the solution sheet also in blue, if you want to take one of those. And I got your programs back and also your written, okay? So I think let's move on. Let's go ahead and move. If you have any questions about the homework, the solutions are there. If you still have some questions, you can come see me, about the exercises in the program. Okay, now at the end of class last time, we discovered the 2's complement rule. Do you remember how that worked? We were trying to store what kind of values? What kind of values were we trying to store whenever we used the 2's complement rule?
Negative values.
Yeah, negative. We needed a way to store negative values. So in the terminology is these are signed integers as opposed to unsigned integers. All right, and we said that the way that worked was to have I think I have a slide here actually. Yeah, here's a slide, figure 3.8. The way we said to do it would be to have this have this bit cell. This is a 1, 2, 3, 4, 5. This is a 6-bit cell, and whenever you store signed integers, the first bit is reserved for the sign. And what was the rule? If it's 0, it's what?
Negative.
Is that what it was?
It's positive.
If the sign bit is 0, it's positive or 0. It's non-negative. Right? Whereas if the sign bit is 1, what is it?
It's negative.
It's negative. So, but then there was something interesting. We didn't just take like the way we showed how to store -5, and we didn't say you just take 5, positive 5, and then just put a 1 in front of it. That's not how it worked. Why didn't it work that way? Because what do we want to have happen in the circuitry with the adder? What did we want to have happen? Yes, when we added together 5 and -5, we want it to be 0. Right. Does everybody remember that, how that worked? So we went through and we discovered, to have that feature, we discovered, as we show here, the 2's complement rule, the way you negate a number in binary is you not the number. In other words, you turn all the 1s to 0s and the 0s to 1, then you add 1. And then that's the negation. And this will guarantee you to give you a 1 in the sign bit, by the way. Guaranteed. All right. Now, let's suppose that we have a 4-bit cell over here. So let's suppose we have a 4-bit cell. So what our cell looks like, it's like this, and this part of the cell is the sign bit. Now what I would like to do is let's do a few numbers. Okay? So can you tell me, first of all, how would you store 0? Let's do 1. How would you store 1 with these 4 bits?
0, 0, 0, 1.
0, 0, 0, 1. How would you store 2?
0, 0, 1.
0, 0, 1, 0. Is everybody clear? Okay. Now let me ask you. Oh, and how would you store 0? 0, 0, 0, 0. Now how would you store -1? What's the rule? So over here, what's the rule? So you take the
1's complement.
Yeah. So first of all, you'd write down what 1 is, which is what?
0, 0, 0,
0, 0, 0, 1. And then what would you do with this? You would flip. You'd flip all the bits. Are you with me? So that would be 1, 1, 1, 0, and then do what? Add 1. And when you do that, what do you get? 1, 1, 1, 1. So isn't this interesting? That -1 is 1, 1, 1, 1.
So 1, 1, 1, 0 is not 1. It's not 0, 0, 0, 1. That's the notation is not.
Yeah, this is the negation of this. Neg here.
Neg is 1111.
Here, let's write what it is. Neg this is 1110.
No.
Sorry.
not that.
That's not, yeah, my mistake. So, not, yeah, it's not neg. So, not 0001 is 1110, right? So the way you get -1 is you take the not and then you add 1 to it, and that's this. So over here on our chart, -1 is 1111. Does everybody see that? Now let me ask you, what about -2? What do you suppose that's going to be? Let's come over here. So now what do we do? Well, how is 2 stored? Okay, so here let's do it stepwise. So 2 decimal is what binary?
0010.
0010, right? So now so what's the recipe? We do not 0010, which is 1101. Are you with me? So we have 1101, and then we add 1. So now what's this going to be? Now check this out. 1 plus 1 is
0.
carry your 1. 1 plus 0 is 1, and then 1, and then 1. That's it. So over here, this is 1110. That's how you store -2. This is how you store -2. And notice that as advertised, there's a 1 in the sign bit. Now, can you tell by this pattern what -3 would be?
1101.
Actually, what happens as you go from here to here? What are you always doing?
Adding 1.
You're adding 1.
You're taking away.
So you're adding 1, add 1 to get to here. And notice what happens if you add 1 to this.
Yeah.
You get, notice how it works even across this boundary? Yeah? So what do you have to add
You're subtracting.
1 to get this? What would this be?
1101.
Yeah. Does everybody see? Because if you add 1 to this, you get this. And then -4 would be what?
1100.
And -5 would be what?
101.
Yeah.
1011. -6 would be what?
1010.
1010. -7 would be what?
100.
1001.
1.
Is that right? Now let's verify that this -7. Let's verify this -7. So let's come over here. So check this out. 7. So 7
Is 0111.
decimal equals 0111 binary, right? Unsigned. And so if you negate this, you get 1000, and then you add 1 to that. Are we good? And that's 1001, right? Now tell me, what's the largest positive number that you can get up here? So let's do ... What's the biggest positive one?
7.
It's 7, right? Because it's, so here if we do 7, that's 0111. So does everybody see that the way we get -7 is to negate this and get to this? Now what little phenomenon do you notice here? What strikes you as interesting about this range of numbers that we can store? Can we store, so what's the range? Can we store anywhere from -7 to 7?
Could you go to -8?
That is an interesting question. Could you go to -8? And the answer is, why not? But there's something curious about -8. There's no corresponding what? Positive 8. Do you see what we're saying? But if we are to store -8, what would it be? -8 would be what?
1000.
1000. Now, here's another interesting phenomenon. What should happen if we negate 3? What should we get? We should get, if we negate -3, what should we get? We should get, well, let's check to see if that's right. Okay, so over here. So here, here, -3, so just from our chart over there, -3 decimal is, if we use, assuming 2's complement, then what is it with those over on the,
Switch it first.
well, first of all, let's write down what -3 is.
1101.
1101. So, and that, we get that from this, what we just did, right?
Yeah.
Is everybody good? So now, how do you negate this? How do you negate a negative?
Subtract one.
Subtract one first.
No, Whoa. What's the rule?
Oh, okay, so you want to do it the same way.
We want to do it the same way. We want to do it the same
Take
way.
its complement.
So,
0, 0.
yeah, so not this, so that's 0, 0, 1, 0. Are you with me?
Add it.
And then 1, add, and it works, 0, 0, 1, 1, because this is 3. Now, do you see how that worked? You negate a negative the same way you negate anything. You flip the bits and add 1. Right? But now, you guys, what about negative 8?
It will be 0, won't it?
Well, check this out. What's negative 8 decimal?
1000.
1000. I hesitate to call it 1,000 because because it's negative this many. I mean, it's not. Yeah, okay. But now, what happens if you try this rule? What happens if you try to negate negative 8?
0, 1, 1, 1.
Yeah, this would be 0, 1, 1, 1, and then add 1. Are you with me? Is everybody following this? But now, what is this? 1 plus 1 is what? 0 carry 1, 0 carry the 1, 0 carry the 1, 1.
It's negative 8. It's interesting.
Now, yeah, see, but this, what did we get back again?
Negative 8.
We got negative 8 back again. But here's the, why did that happen? Because there is no positive 8 to correspond to it. Do you see what I mean? So over here with this table, if you negate each one of these negative ones, you'll get the corresponding positive one. But this is the exception to the rule. And the reason it's the exception is because it's an exceptional value because it doesn't have a corresponding positive value on the number line. Are you with me?
Yes.
Yeah.
Just a quick question. With all the other negative values, say, and even the positive ones, but it's less illustrative, we don't count the first cell towards the value, but with negative 8 we are.
Because we count those as the
Wait. What do you
We
mean?
don't
What do you mean we don't count?
Like take negative 4. We have 1, 1, 0, 0.
Take negative 4, 1, 1, 0, 0, yeah.
Not the same,
But that's
right?
not, an 8 plus a 4, it's just a 4 and it's negative.
Well,
We're not including
But
the
that rule
sign
doesn't
bit.
go for the rest of them either. Like, that doesn't work for negative 5 if you don't include the first one and add the last 2.
hold on. Hold on, yeah. Well, yeah. You bring out an interesting point. How do you determine
It's like both
how-
the sign bit and counts toward a value, but only on some of them.
No, what do you mean counts the value? I mean, okay, let's come over here. Let me show you. Here. Let's do a little bit bigger number. Okay, a little bit bigger cell. Suppose we have a 7-bit cell. And suppose I ask you, how would you store negative 13? Now, how would you figure out how to store negative? How would you store negative 13 in a 7-bit cell?
Would you write it for 13?
First, you would write it for 13, and then you would take the 2's complement. So let's do that. So how would you store 13? 0, 0.
0, 1. Was it 1, 0?
Well, what's 13? What was that little rule that we had?
Divide.
Divide by 2. Can you do that real quick and tell me what it is?
The right side.
So it's
Can you? Somebody do that real quick.
Right to left, it's 1, 0,
Can
0, 0, 0,
0.
1, 1, 0, 1.
Yeah.
There you go. I'm happy.
Okay. Now, and you can do this by doing that little remainder trick, right? But now, is this right? Because this is 1, 2, 4, 8. 8 plus 4 is 12, plus 1 is 13. So this is 13. So how is negative 13 stored? Well, 1, 1, 1, 0, 0, 1, 0, and then add 1. So it's 1, 1, 1, 0, 0, 1, 1.
Okay.
Okay, so this is how negative 13 is stored. Now, suppose I give you a binary number. So let's go over here. Suppose I give you, with this 7-bit cell, suppose I give you 111001 and ask you, what number in decimal is this?
The same thing, you just,
One way to do it is to flip the bits and add 1, and that will give you a positive number, so you know this original one is the negative of that. Are you with me?
yes.
But would you like to know a slicker way? And this gets back to your question, what cells do you count?
Right.
Now watch this, you guys.
First and subtract the last.
No subtraction. Watch this. Are you ready for this? What you do is, instead of adding the place values of the ones, what do you do?
Zeros.
You add the place values of the what?
Zeros.
Of the zeros. Are you with me? But then, because of that 1, you're off by 1. So you have to add 1. Are you with
Well,
me?
if there are no zeros,
So,
Then you get
well, if there are no zeros, it's 0 plus 1 is 1, so it's negative 1. Okay, so watch this. So which place is this? Which place is this? This is the 2's place, right? Which place is this? 1, 2, 4. This is the 8's place. So you have 2 plus 8, but then you have to add plus 1. This is this extra 1. So this is 11, which means that this is negative 11. Oh, that was a bad example because 11 is 1, 1 in decimal. But anyway, so 1, 1, 1, wouldn't you know it? Pull an example out of the air at random. 1, 1, 0, 1, 0, 1 binary equals negative 11 decimal. Fortunately, we have this notation decimal, so we know this is a decimal number.
cool.
Are you with me? And if you want to, you could double check, you could verify this by flipping all these bits
And add 1.
and adding 1, and that should be 11. Right? Now, let's come back over to here. What's one thing that we notice? There are some special values that we should notice. First of all, no matter how many bits there are in the cell, how do you represent 0?
Zeros.
All zeros. No matter how many bits there are in the cell, what's the largest positive value you can store?
No, except for the
A 0 and then all ones. Are you with me? No matter how many bits in the cell, how do you store the smallest number?
1 and all zeros.
1 and then all zeros. And no matter how many bits there are in the cell, how do you store negative 1?
All ones.
All ones. Now, is everybody clear on that pattern? Okay. So over here, we see, if we were to work this out, figure 3.9, with a 4-bit cell, we can see how to go all the way from negative 1 to negative 7, but then we can say, well, let's include another value because that bit pattern wasn't included, so it goes from negative 8 up to 7
So that's
in
the
figure
range,
310. Yeah, that's the range for a 4-bit cell. It's an exercise for the student to figure it out in general. What's the equation to?
Will it always be 2 to the number of bits?
Yeah, that's what you have to figure. Yeah, you figure that out. Yeah.
Because it's 16.
Yeah. Okay, and here's this trick. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Figure 3.11 is a 10-bit cell, and here's a big number. Now, can you tell me from figure 3.11 what this number is? First of all, what do you inspect? The first thing you inspect when I give you a big bit number and the cell size, what's the first number you inspect? The first spot, the sign bit. If it's a 0, you just do the place values for the, and it's just a positive number. But if it's a 1, then what do we do here? How big is this number?
38.
Is that right?
Negative
32. Okay, so this would be 32
plus 5.
plus 5 is 37, plus 1 more is 38. So that number must be
Oh, negative 38.
negative 38. Is it even? Is negative 38 even?
Yeah.
What do we have for the least significant bit? 0. So that works too. It remains true for negatives. Are you with me? Is everybody clear? Now here's one way to think of it. These next two figures, here's one way to think of it. We have these, let's suppose that we have a real small example here. Suppose we have a 3-bit cell. So in a 3-bit cell, if you consider the number to be unsigned, what's the range? You can go anywhere from what to what? From 0 to 7. Does everybody see that? Here's 0 to 7. But now, if you want to consider that bit pattern to be signed, then what do? You reserve the first cell to be the signed bit. Right? So in that case, what's the smallest what's the largest positive number? It's 3. Right? So look, what in effect, so if we take a look at figure 3.13b, now what happens is the largest positive number is 3, and basically what happened with all those bit patterns that have a 1 in the first bit? Those now correspond to the negative values, do you see? And so those negative values, it's like you break the number line in the middle and you shift those, you use those bit patterns that you can't use anymore because there's a 1 in the sign bit, but it's just really the number line shifted over. So as you go from left to right, each time you go one more slot to the right, you're always adding 1, even as you go through the 0. Does everybody see how that works? So this is another way of viewing the number line whenever you do signed numbers. You basically take roughly half of the bit values that had a 1 in the sign bit, and now those numbers are going to be negative. So those patterns are, you use all those bit patterns. But now you use them for negative values. So look, you guys, here's an important concept. This is really important. This is something that a lot of people have a hard time grasping. What are the 4 parts of a computer? Input, CPU, memory, and output. What does memory do? It stores bit patterns. All right? Now look, you guys, what does that... when you store a bit pattern in main memory, in a cell in main memory, how do you know whether that bit pattern is a signed integer, an unsigned integer, or an ASCII character? How do you know? How does the computer know what it is? Trick question. How does the computer know what kind?
It doesn't.
It doesn't, yeah. It doesn't know. All it does is it just remembers. So it's up to the software or the programmer of the software to interpret that bit pattern whatever way possible. Are you with me? Mm-hmm. Now tell me, and now here's another, that's one point. Now here's another thing. Where does the addition take place? Whenever we add these numbers, where does the addition take place? In the CPU. Inside the CPU, there is an arithmetic logic unit. Okay, it's an arithmetic unit. And this arithmetic unit adds bit patterns. Now here's my question. How does that adder in the CPU know whether it's adding a signed integer or an unsigned integer? Trick question. It doesn't. It does it the same way regardless. Are you with me? Is everybody clear on that? In fact, it's possible in machine language to add a bit pattern that, at one point in time represented the bit pattern for an ASCII character and do all kinds of, things with it. Okay? Because all it knows is it's doing that operation on that bit pattern. Okay, so with that in mind then, what the CPU has is 4 special bits. Now do you remember this one special bit that we learned about last time?
The C.
It was the C bit, it was the carry bit. But now that was just one of 4 special bits as illustrated on this slide, the status bits. There are actually 4 bits. The 4 bits are N, Z, V, and C. So that C bit was the last of these 4 special ones. All right? Now, and let's take a look at the last, the one, the C. Let's review that. What does it say here? C equals 1 if a what? Unsigned integer overflow occurred. C equals 0 otherwise. Now, do you remember how that worked? If there was a carry out of the leftmost, boom, then that was 1. Yeah? All right? But now, here's the thing. If the numbers are signed, then the conditions for which there is an overflow are different from if there's an overflow if it's unsigned. And so we have to investigate that. All right? And the special bit that is used to indicate if a signed overflow occurs is the V bit. V for what? Overflow. Are you with me? Okay? Because you wouldn't want to have O, because O looks too much like 0, right? So the O bit would be bad. I mean, you'd say O, 0, are you with me? So V, C stands for carry.
Oh, right, okay.
Okay, so C is carry, V is overflow, all right? And then, in addition, it's sometimes, whenever you want to test a condition of whether it's positive or negative, then there are two other bits. They are, the first one is the N bit, and what do you suppose N stands for? Negative. So notice what happens is N equals 1 if the result is negative, N equals 0 otherwise. And then the other one is Z. Z stands for? 0. So it's the negative, the 0, the overflow, and the carry bits. So, and the 0 bit works as follows. If Z equals 1, if the result is all zeros, and Z equals 0 otherwise. All right? Now what we're going to do is we're going to do a series of examples, because whenever you do an addition in the arithmetic unit of the CPU, not only does that addition take place, but all 4 of these bits are set accordingly. All right. So for your assignment for next time, you have a series of additions, binary additions that you have to do, and you have to be able to figure out what the N, the Z, and the V, and the C bit are for each one of those. Are you with me? Mm-hmm. Okay. So let's do some over here. All right. Now, and it's kind of, I think we'll have to come up with some rules. We'll have to figure out some rules to see how these bits are all set. All right, so now I think I assigned for you number 20, some additions, and we will do number 19. So number 19, so here we have a 7-bit. Yeah. We're going to have a 7-bit cell, all right? And we're going to add, the first thing that we'll do a bunch of these additions and we'll draw some conclusions. Okay, so the first thing we'll do is we'll add 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, and we will add 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0. So the operation here is add. But after we add, we also have to determine N, Z, V, C. Yes?
There's a significant reason why you would split up the sets of 4 bits, right?
Yeah, it's just visual. It's to keep things straight. Plus, we will see that in a little bit we're going to learn hexadecimal. And there is, with the hexadecimal notation, which is a shorthand notation for representing bits, each hexadecimal digit represents exactly 4 bits. So it's kind of like conventional. It's just
okay.
It's just conventional to keep things. I put a little gap here. You notice this little gap
If
here.
this was converted to hexadecimal, there'd just be 2 places.
There'd be 2 hexadecimal digits. Yeah. So, but it's just visual. Of course, in the computer, there's no space in between this bit and that bit. I mean, it's a lot electronic. Okay. All right. Now, are you okay? So let's go. Now we'll go around. Okay. So
1.
1.
0.
0, carry your 1.
0, carry 1.
0, carry the 1. We carried the 1, right?
Yeah.
So,
Is it 1 carry to 1?
yes, because it's 1 plus 1 is 1, 0, plus another 1 is 1, 1, right? So it's 1, carry the 1.
1.
1, 1,
0.
0. Okay? Now, what is the N bit? How do we know what the N bit
The
is?
last bit?
No, it's not the last bit. Well, it's the first one.
Well, that's what I meant. Yeah.
Oh, right. Oh, you know, actually, that's a good point. Let me give you some terminology here.
Yeah.
In order to keep it from being confusing that way, the unambiguous way to say it is this is the least significant bit, and this is the most significant bit. So instead of first, last, which you know, first which way, this is LSB and this is the MSB.
Okay.
Least significant, most. Basically, so n is what? 0. N is always just a copy of what the sign bit is. Are you with me? Because it's 1 if it's negative. So it's just a copy of that bit. All right. Okay, and what about Z? Why is it 0? Because they're not all zeros. Now, let's do C. How about C?
0.
And why is it 0? Because when we added this plus this, we got 0, and the carry out was 0, right? But now how about V?
I think you wanted to do that the other way.
Assign.
NZVC is always how we do it.
Yeah.
NZVC. But the carry is 0 because when you add this plus this, you get 0, and the carry out of the whole thing is 0. Are you with me? But now what about V? Was there an overflow here?
No.
No.
How do you know there was no overflow? Because what kind of number are you adding here?
0.
No. What kind of number is this?
Positive.
It's a positive. And what kind of number is this?
Positive.
It's positive. And what did you get? A positive. So that means that there was no overflow. Are you with me? Question?
Would overflow only happen if in the second to most significant bit there were both ones?
Not necessarily, not necessarily, but if they are both ones, then there would be a carry.
Oh,
So you see,
at least 2 ones, I should say.
Is V1 if...
well, you could have had a 1 here and a 0 here, and you could have had a carry from the
That's what I'm saying,
previous.
So at least 2 ones, meaning the 1 would be up.
Well, what happens is, what happens is, if this is positive and this is positive, and you have a carry out from this one to this one, that's
The overflow.
If you carried into the sign bit.
yeah, if you carried into the sign bit.
Would
But would it have
the
be C too?
Well, the easiest way to figure this out is if you add 2 positives and you get a positive, you're safe. Are you with me? Okay, let's do another one. Let's do 1, 1, 1. Let's do 1, 1, 1, 1, 0, 0, 1, and 0, 0, 0, 0, 0, 0, 1, 1, 0, 1. So now here we're doing add, and we also have to determine N, Z, V, C. Okay? All right, so let's do it. 1 plus 1 is what?
0 carry the 1.
0 plus, carried the 1. 1 plus 0 plus 0 is what?
1.
1, carry the
0.
0. Okay, 0 plus 0 plus 1?
1.
1. 0 plus 1 plus 1?
0 carry the 1.
0 carry the 1.
0 carry the
0 carry the 1.
0 carry the 1.
0 carry the 1. 0. And now what did you say?
C.
Carry the 1. So we know that C is 1. Are you with me? Now what about N?
0.
0, right? Because that's the copy of the sign bit. Are you with me of the result? Now what about Z?
0.
0, because they're not all zeros. Now what about V? Was there an overflow?
With a negative plus a positive, and it overflowed.
Did it overflow? So do you think V should be 1? Oh, this is interesting. Let's come over here.
Because we're adding a negative and a positive.
Well, yeah. Check this out, you guys. Let's figure out what number this is. Let's figure out what number this is in decimal. The top one. Now, how do we do it? How do you do it? It's 2. Are you with me? 2 plus 4 is 6, plus 1 is what?
7.
7, which means this number is what?
The negative 7.
Negative. So what we're doing is we're taking negative. Oops. So we're taking negative 7. Now, what's this number? It's positive. So what place is it? 1, 4 plus 8. 8,
12,
9, 10, 11, 12, 13. This is negative 7 plus 13. All right. Now, what is this number?
6.
2 plus, this is 6. Well, what happened?
That's right.
It's right.
So V is 6.
So V is 0. Now, does everybody see how that worked?
So do you have to
Think about it. Think Think about it for a minute. How can you overflow when you add?
It's too big or too small?
If it's too big, well, too big one way or too big the other way, too small.
Too small?
It's when you
So
go out of
negative
what
and
you can
negative?
store.
When you can go out of what you can store. But the only way that can happen
Is
Is
if
if
you're
you add two
negative?
negatives?
And you get,
if you add two negatives and you get one that's even more on the negative side, or what?
adding two great positives.
Two positives and you get something that's more on the positive side. Can you ever get an overflow when you're adding a negative and a positive? Never. So right away, the one rule is, oh, if this is in this, you know V is always 0.
I thought if you're adding two positives and you get a positive, then you're fine.
You are. But here, let's do. Here, yeah. If
The
you,
carryover though.
well, yeah, here, let's do some more. Now check this out. All right. So now let's do. Okay, so now let's do 1 0 0 1 0 0 0 1 1 0 and 1 0 1 0 1 0 1. And now let's add this. And we also have to determine N, Z, V, and C. Yeah? Okay, now watch this. 0 plus 1 is what? 1. 1. 0 carry the 1. 1. 1. 0. 0 carry the what? 1.
So then it's 1. Because it's 2 negative?
Yeah, and now, yeah, first of all, let's dispense with this. So Z is what?
0.
0. N is what?
0.
0, because that's a copy of the sign bit. 0, because these are not all zeros. But now what about V? What are we doing here? We're adding a negative
And a negative.
and a negative, but we're getting a positive. So we know that's an overflow, so that makes V 1. That means V has to be 1 after that.
And that works the same for two negative numbers, right?
We did two negative
If
numbers.
you get right, two positive numbers. If you get a C and you have two positive numbers,
Well,
it will be guaranteed.
Wait. The C has nothing to do with the V.
If you are adding two positive numbers and you get a negative number, then
Yeah, okay, in fact, let me do one more adding two negatives. Here, let's do another one. Let's do another one adding two negatives. Let's do 1 1 0 1 1 0 0 0 0 1 and 1 1 1 0 1 0 1. And let's add these. And let's determine N, Z, V, and C. Is everybody, are you with me?
0 carry the 1.
Okay, so now 0 carry the 1,
1.
1,
1.
1,
0.
0.
1.
1,
0 carry the 1.
0 carry the 1,
1 carry the 1.
1 carry the 1.
1, but now it's carry the 1, right? So that's 1 here for the carry. Is everybody clear? And what about N?
1.
It's the copy of this bit. The result is negative, so N is 1. Are you with me? And Z is what?
0.
0, because they're not all zeros. So that's 0. But now what about V?
So we had two negatives and we got a negative?
Yeah. So did we overflow, yes or no?
No.
No.
No. So what is V?
0.
0.
Cool.
Are you with me? And here, do you want to figure this one out over here? So look. What is this number?
That.
That is, now, how do you do this? 2 plus 4 plus 8 plus 16 is what?
29.
It's 30.
Wait. 2 plus 4,
6.
6 plus 8
14.
plus
16.
16.
30.
It's not 30. Because I added a 1 on it too.
So that's a negative.
Oh, and then plus an additional 1 is what?
Negative 31.
It's 31, so this is negative 31. Is everybody good? Now what's this one?
2 plus 8.
2 plus 8 is 10, plus another 1 is 11. So this is negative 11. And now what is this one?
1.
1
Plus 8 plus 32.
plus 8 plus 32.
Plus 1.
plus an additional 1.
Which is 42.
So that's 42?
Negative.
So this must be negative 42. Is that right? Yeah, we added negative 31 plus 11 and we get negative 4, so everything's fine. Now, on the other hand, if we were to interpret this as an unsigned number, what number would it be? Well, it would be it'd be 1 plus 32 plus 64, and this one would be 1 plus 4 plus 16 plus 32 plus 64. And when you add those up, it would overflow. But so you see, the circuitry doesn't know whether you are interpreting this as a signed or an unsigned number. The circuitry just does this and sets the bits. It's up to you, the software. So what happens is, if you're writing software to do this addition, you would, after you do the addition instruction, you would test these bits to see whether or not you want to declare that it was an overflow.
Okay.
Does everybody see how that works? Okay. And I don't know, I think there's a couple of other ones, but I think you get the idea. All right? Does everybody see how to do these? All right. Now, the next thing that we have at the, what does ISA stand for?
Instruction set architecture.
Instruction set architecture. Which level is that? Number what? That's number 3. Oh, you memorized them?
Not the greatest. I know that one.
You know that one.
Someone did work over it.
Or level 6.
Okay. Now, in figure 315, we have 3 more operations, okay? These 3 operations are AND, OR, and
Exclusive OR.
exclusive OR. Exclusive OR is denoted by the letters XOR. And in the instruction set, or one of the operations that the computation unit can do that's in the CPU is it can do these logical operations as well. So therefore it's called, the unit is actually called here, the unit is actually called an arithmetic logic unit. Okay, and the acronym is ALU. That's what the circuitry is called. And it does, the reason it's called an arithmetic logic unit is because it does both arithmetic and logic. What we've been doing before with the addition, addition is by far the most common arithmetical operation that's done. It's done all the time, okay? So it's a really important operation. Lots of, the computer science, computer engineers, they know everything there is to know about how to do, addition fast. If and when you take the computer organization class, we will actually build one with circuits. We'll actually build an ALU. Okay, now, and so we'll see some of the algorithms that how that happens in the hardware. But in addition to the arithmetic operations, it also does these logical operations. Now you know these from formal methods, right, already. So you know how AND works. Basically what happens is, at the ISA level, information is stored in binary as 0s and 1s, and if you interpret 0 as false and 1 as true, then then that's the truth table for the AND operation. Are you with me? So the way the AND works is P and Q is 1, if and only if both P is 1 and Q is 1. For all other combinations, it's 0. So that's what is true and false?
False.
False. So what is 1 and 0? 0. Are you with me? That's how that works. And then same way with OR. Only with OR, what does the truth table look like? It's, well, not the opposite, not the negation, but if one or the other or both are true, then the OR is true. Mm-hmm. So it's only 0 if they're both false, if they're both zeros. P and Q are both 0. And XOR stands for exclusive OR. And what's the difference between exclusive OR and OR?
They can't both
That's
be.
where they can't both be.
Yeah, it's if one of the inputs is true exclusive of the other one. Yeah? So that's the XOR. Now what happens then is, and these are bitwise operations. So whenever you do, and here's the correspondence, this figure 316. This is the correspondence between 0 is false and 1 is true, right? Now, but now whenever you do this, whenever the CPU does this, it does it bitwise, right? So here, let's take this computation, 1000110, 1000110, not this computation, but this number, and 1010101, 1010101. Now, and let's AND this. Now, whenever you AND these, you AND them bitwise, but now here's the thing. There's no concept of a carry, and there's no concept of an overflow. But you can still test this to see if the result is either what? All zeros or has a 1 in the sign bit, right? But the concept of carry and overflow doesn't make any sense. So the only two bits that are affected whenever you do an AND are N and Z. Do you see what I mean? Mm-hmm. So V and C are unaffected whenever you AND, whenever the computer doesn't AND. So let's just do it. So what would this be?
0.
0,
0,
0, 1,
0,
0.
0, 1.
N is
1.
1, Z is 0. Yeah? And let's do the OR. Here, I'll tell you what we'll do. I have an eraser. So I can just do OR. But you have to write more.
1, 1.
Okay, yeah, so this would be what? 1, 1, 1, 0, 1, 0, 1. And this, and then here again, N and Z.
N is 1.
1,
C is 0.
C is 0. Are we good? And again, I'll use my trusty eraser, but unfortunately you have to write it all over again. Oh, and I can even put an X here and reuse my OR.
Okay, 1.
Okay, so yeah, now what is this? This is 1, 1, 0, 0, 1, 0, 0. Is that right? N, Z.
0, Z equals 0.
Yep. Does everybody see how that works? Okay, good deal. Oh, now, shoot, I wanted to do one more thing because you have a program due tomorrow, a Java program.
Due Thursday.
Thursday rather, not tomorrow. Do I have time to demo? Okay, here comes our demo. Are you ready for this quick demo? Okay, here is our demo. I'm going to do this demo offline because didn't quite have enough time to finish it during the main lecture, so I'll record this for posterity. So first thing we're going to do is I want to demo what the application should do in this problem 3.57. So here's our problem 3.57. I have this SOL, that's my solution. And let me just run the app to show you how it works. So we'll run it here. And notice what happens is up here in the upper left we have a dialog box. It has some elements in it. First of all, it has a label, problem 3.57. Then there's some instructions here. Enter an 8-bit binary number and a field to do our input, and then a button here that says print the next 10 numbers. So we'll start with, let me just make up a number, 0, 1, 1, 1, 1, 1, 0, 0, 0. Now let me stick in an extra bit. How many bits do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This says enter an 8-bit number, but I have entered a 10-bit number. So let's click this and see what happens. Oh, here we get this error message. Enter exactly 8 bits. So you see there's a little error checking there. So let's enter exactly 8 bits now, all right? So now we have 0, 1, 1, 1, 1, 1, 0, 0. That's 8 bits. Now when we click print the next 10 numbers, boom, here's our output. Let's scroll up here so we can see it. And so you see it says enter exactly 8 bits, and then it starts off with the number that I entered. Here's the app. Here's the dialog box for the app. So I entered 0, 1, 1, 1, 1, 1, 0, 0. So it starts off 0, 1, 1, 1, 1, 1, 0, 0. And notice that what it does then is it counts. It counts up the next 10 numbers. So if remember, we learned how to count in binary. So this is 0, 0, and then 0, 1, and then 1, 0, and then 1, 1. And then it goes up 1, 0, 0, 0, 0, 0, 0, 0, 1, 2, etc. Now here's an interesting feature that your program has to do. Let's cancel this, and we'll clear this. Okay, and let's run the program again. All right, now this time let's enter 1, 1, 1, 1, 1, 1, 0, 0. And now when we ask to print the next 10 numbers, notice what happens. You see, if you get all the way up to, here's 0, 0, 0, 1, 1, 0, 1. Now they're all ones. So if you get up to all ones, it should just cycle through and go and start off at 0, 0, 0, 0, 0, 0, 0, 0, and then 1, 1, 0, 1, 1, 1, 0, right? Okay, so that's the demo of what the program should do. It should create this dialog box with a label, enter an 8-bit binary number, and then you enter the user enters the number and clicks this button that says print the next 10 numbers. Okay, now so that I don't show you the solution here, what I'll do is I'll go to problem 0357, and we'll take a look at the code of what's available to you. Okay, so here's the code. We'll double click on this. All right, so here now this code that I'm showing you now in this problem 0357 main.java, this is what's available on the web page, on the course web page. And so you can download this, and what I've done for you is I have done all the Java that sets up the dialog box with the label and the input field and the button, and then all you have to do is fill in the code to do the actual counting through in binary. So let's take a look at what this code looks like. Okay, first of all, we have a bunch of imports here. Okay, and this AWT stands for Abstract Windowing Toolkit. That's a library, a common library. And then this swing is a different library that adds on to the AWT. So these are and I'll let you refer to the Java documentation for what these classes are, these libraries that we want to import. And then the way Java works here is we have public class and then prob 0357 main. So this is the name of the class, and it is stored in a file named with the exact same name as the class. So in Java, the files have the same name as the class, and the suffix is .java. So notice up here in the documentation, we have the documentation that says this is in file prob 0357 main.java. And it's problem 3.57 of our textbook. Okay, and then what this class does is it implements action listener. So here again, I will refer you to the Java documentation on what that means. But this is how you set up a main program class that uses a graphical user interface. Now we could have used a graphical user interface for the output as well as the input, but I think it's simpler for all the problems that we will do in this class to have a graphical user input for the input, but just to use the console, the console for the output. So now you recall in that in the dialog box. Here, let's bring that dialog box up again. Okay, so here's the dialog box. It has first of all, there's the dialog box itself, and so this dialog box itself is like the main window frame, and then the input panel is this part of the dialog box here, and then the J label. So J label is the class, that's the type, and then label is the variable. So this label is this label, enter an 8-bit binary number. The J text field is the type of this next object, which is called text field. So the text field is this that we input where we input our data, and then there is a button panel, and then the button itself is the button that contains this print the next 10 numbers. Okay, so that's what these variables correspond to. They correspond to that part of the input dialog box. And then under Prop 0357 main is which is the main program for so the class is Prop 0357 main, and then Prop 0357 main. So this is a method that has the same name as the class. So this method is the constructor. So what we're doing is we're doing the constructor to set up that dialog box. And here I don't think I'm going to spend too much time going over the code, and it's kind of obvious based on the names of the variables, what's going on here. And so here we have some documentation. This is the code to set up the main window. So we allocate a new J frame, and for the constructor for the J frame, we give it the text that we want to appear in the heading of the dialog box. You noticed it said problem 3.57. Then we do some more things here. We set the size. This is the size in pixels. And then the next section of code, we lay out the label and the text field input panel, and this goes from top to bottom. So first we do the J panel, and there's some layout details that we don't have time to go into. I've done this all for you. And this text, here we allocate our label gets new J label, and here is the text that goes inside the button that we pressed where it said enter an 8-bit binary number. Here's the text field itself, the size of it. There's this some border issues. You want to make it look good. You can look up the documentation on what this means. And then we actually physically lay out, we are programming the layout here. So this is not like Qt where we can drag and drop the GUI elements. Instead, we're actually doing it we're actually laying out the dialog box in the code, in the constructor code itself. And so here we set this layout, and then we have some borders that we add, and we've got this horizontal glue, and I'll let you read all about that in the documentation if you want to. And then here is the button says print the next 10 numbers. This is the text that goes inside the button. And then we combine the input panel and the button panel in the main window. So we add this, and we have it centering, and things like that. And now here, this code adds the method here is called add action listener. And so what this code does is it determines what happens whenever the user interacts with the GUI elements, the graphical user interface elements. And the reason we have a listener for the text field and for the button is because we want the ability, we want the action to take place. In other words, the counting up of the numbers to take place if the user clicks the button, or if he's entering text in the text field and presses return. So we want our action to happen with either one of those two, and so that's why we have these two add action listeners. Now there's a warning here. It says leaking this in constructor, and for now I think I researched this, and it's a little obscure. It's safe just to ignore these warnings for our purposes. Okay, and then some other cleanup stuff here. All right, and then we have this method called create and show GUI, and so this what this does is, what we looked at was the code for the constructor for the main, and so here we actually allocate the main window, and then this main is the program that executes whenever we start the our application, our GUI application, and then there's some more code here that's I'll let you read about that gets everything started. Now the main thing that you have to understand though, or that you have to do when you program this, your assignment, is there is a method here called action performed, and the parameter that is passed to it is an event. Well, it's an action event. The formal parameter is called event, and this action performed gets called whenever you either click the button or whenever you have entered text in the text field and press return. So all of this code is posted on the web page for the course, and it's all you need to do is fill in this part right here, okay, where it says problem for the student. And let's take a look at what action performed, what action happens whenever you click the button or whenever you press return after entering some text in the text field. First of all, there is a variable here called bin_num, which stands for binary number. And over here, we see its type is int, and then we see these square brackets. Okay, so what that means is that bin_num is an array of integers, and we allocate this array of integers by saying new int 8. And the reason we say new int 8 is because there are 8 cells in the bin_num array. So there is a bin_num sub 0, a bin_num sub 1, a bin_num sub 2, ... all the way up to a bin_num sub 7. So there are 8 cells indexed from 0 to 7. So this is just like C++. I mean, you guys know C++, and so this is just like C++. Now, the next variable that we have is a variable called line. Okay, and this line is of type string, capital S string. Now, capital S string is a Java type that's provided by the standard Java library, and line is so what line does is line. What we do here is we say line gets text field dot get text. So what this does is it inputs the text that the user entered in the GUI field named text field, and there is a method associated with that field that's called getText. So we call that method from that field, and it does exactly what you would think it would do. What it does is whatever text the user entered in that text field, line gets that. And what is line? It's a string. So now the input, this is how we get the input from the dialog box into this variable named line, which is a string. Now, line is an array, or you can treat it as if it were an array, and the first thing that we do, but instead of being an array of integers, it's an array of characters, right? So there is a line sub 0, a line sub 1, a line sub 2, and so on. And I will let you look up in the Java documentation that's online, you can look up the methods that an object with class string has, and to see how to manipulate the characters in that string. And so the first thing that we do is we say if line.length equals 8. Well, do you remember when we did the demo a few minutes ago? We put in 10 characters and then we pressed the button. Well, it called this action perform. It allocated this array of integers, and then this line got that string of characters, 10 of them, and line.length was 10, so it wasn't equal to 8. So therefore, that's how it printed out this system.out.printf, enter exactly 8 bits, and then output a new line. Of course, now what you should do with this problem for the student is, what you need to do is convert the array of characters to an array of integers. So you need to go through this line, and wherever there is a character 1, you should make it an integer 1, and wherever there's a character 0, you should make it an integer 0, and you should store those integers in binnum, in this variable binnum. And then after you store those characters in binnum, then what you should do is you should print out binnum and then add 1 to it, and then print it out the next number, and then add 1 to that, and print it out and add 1 to that. Now, of course, how do you add 1 in binary? Well, you add 1 to the least significant bit, but then you carry, like 1 plus 1 is 0, carry the 1. So you're going to have to worry about, you're going to have to calculate how that carry gets propagated over to the left as you add 1 to it each time through. Okay, so I hope this should get you started okay. Like I said, this text, this prob0357 main.java is available on the web page. Is all you have to do. You can read through this GUI stuff, but we're not going to deal with the GUI stuff very much in the course. I'll let you learn that on your own if you want to. Otherwise, I've provided it here. Is all you need to worry about to get the problem done is the code for this part of action performed. All right, and that's the end of the demo, okay? And that's the end of the lecture, and so see you on Thursday.